I'll say it again. This is Unit 6. Rotational energy and momentum. All right? So, I want you to imagine I have a potato that's just in space someplace, a space potato. And let's say, for argument's sake, that the potato is just tumbling in space. Again, so we have our space potato, and it's just tumbling end over end in space. The space potato has an axis of rotation that's right about there, based on what we just saw. Now, I don't know about you guys, but I do like potato salad. So I want you to imagine that you could dice up this potato, and there are multiple pieces. But let's say we dice it up, but we put the whole thing back together so that there's many pieces of potato. This is piece number 1, piece number 2, and piece number 3. Now, the whole potato is tumbling with an angular speed of omega. So some kind of radians per second or rotations per second. Now, piece number 1 is a distance r1 from the axis of rotation. And if you'll recall, it being where it is, it must have a velocity that is based on how far away it is from the axis of rotation. Right? Because we know that v equals omega times r. So things that are further away from the axis of rotation are rotating faster or moving faster than things that are close. And there's also, m2. M2 is a distance r2 away from the axis of rotation, but it's so much closer, its velocity is going to be way less because it's much closer to the axis of rotation. Remember, the piece that's at the axis of rotation is just spinning. It's not got any velocity, just spinning in a circle. And then there's piece 3 chilling over here on the other side of the potato, and it's got its own velocity. It's probably somewhere in the middle of the other two. Good so far? Each one of these pieces has kinetic energy. So piece 1 has that much kinetic energy. Piece 2 has this much kinetic energy. Piece 3 has this much kinetic energy. And so on and so forth until we get all the different kinetic energies of the entire potato. Right? We just add them all up. Right? There's lots of pieces to the potato. I couldn't possibly list them all. But for every piece of potato, each one of those would have a different kinetic energy. Yep? Because I'm not thinking and I'm getting tired and I'm thinking about the good old days when I'm not going to be here. Because it's the weekend. So thank you for correcting me. I appreciate that. Now, just think about this for a minute. The entire potato has the same angular speed. So I could rewrite this in terms of the angular speed instead of the linear speed, meaning I could do this substitution here. For example, piece number 1, I could write that as 1/2 m1 omega r1 squared. And for the second piece, I could do 1/2 m2 omega r2 squared. For the next piece, m3 omega r3 squared, and so forth for every piece of the potato. Everybody okay so far? All right. Do you notice that every one of these pieces has a 1/2 in it? I noticed it. Do you notice it? Okay. So I'm going to pull out all the 1/2s. Pull them out front. Do you also notice that every one of these terms has an omega squared in it? Right, do you see that? So I'm going to have an omega squared out here. I'm going to pull it out to the other side. All right, because every term has a 1/2 in front and an omega squared in it too. Is that okay, Betty? All right. Now, look what's left. I take away the 1/2, I take away the omega, I have m1 r1 squared. Take away the 1/2, take away the omega, I have m2 r2 squared. Take away the 1/2, take away the omega, I have m3 r3 squared. Now, I don't know if you're able to see what I'm trying to communicate, so let me get rid of all this distraction for just a minute and kind of rewrite this more carefully. We added up all the kinetic energy of every piece, and we got 1/2 on one side, and on the other side we got omega squared, and in the middle we got m1 r1 squared plus m2 r2 squared plus all the different masses until we get to the last piece and it's squared. Do these look familiar to you? It is. I would write this as the summation of mi ri squared, starting with piece 1 and ending with the last piece. We have a name for this. We called this the moment of inertia. Good job. What it means is every piece of the potato has kinetic energy, but we can think of the potato as one object with one moment of inertia, and its kinetic energy isn't based on the individual pieces, but by the whole shape of the whole object. This is rotational kinetic energy. All right, folks.